Hello everyone, welcome to EN4593 Autonomous Systems module. In this lecture, we are going to look at recursive state estimation. Here is the outline. First, we will have a recap on what we studied last time. The main topic for today is state. So we will look at state variables and how state changes with environment interaction, state transition, what complete state is, and finally, the concept of state estimation. Next, we will revisit some probability theory, and finally, we will have a look at the Bayes filter together with an example. In the previous lecture, first I gave you the course outline. Then we understood what an autonomous system is. Some examples for autonomous systems were discussed after that. Next, we had a look at the paradigm shift from model-based to probabilistic approach. So in model-based, we trust the model. In behavior-based, we trust the observations, and in the hybrid mode, we trust both the model and the observations. And in the probabilistic approach, we neither trust the model nor the observations. Then we recognized uncertainty as the main barrier to develop successful autonomous systems. And finally, to make autonomous systems feasible, we had a look at the probabilistic approach. All right. Now we are ready to have a look at the state. So what does it mean by state? The state is the condition of a system and its environment, or in other words, it is the collection of all aspects or variables that describes the system plus the environment. Now it is very important to note that there will be an internal state in the whole dynamical system that we cannot sense directly. What we will be doing is trying to maintain our own belief about this hidden state with whatever the information we have. We will usually denote state by X, and the subscript T means that it will change with time. Okay. Remember that this xt is not the real or true state of the system, but it is our belief about it. Now if we take an example of a mobile robot, let me take mobile robot as an example. We can have variables that describes that system, such as position, velocity, acceleration. Then it can have a heading direction. If the mobile robot has an arm, it will have joint angles. Then there will be a battery to power the robot, so we can have battery state. And we can also think of whether the sensors are broken or not, right? Sensors broken or not, and many more. Of course, there will be many variables that should describe the mobile robot, but depending on the requirement, we will choose certain variables, right? So this we call as state variables. States can be continuous. So if we take position, velocity, acceleration, we have a continuous profile for them. But then again, the variables can be discrete as well. So in this case, sensors being broken or not, that can be a discrete variable, or a mix of these, right? A hybrid state. Now, if I ask you, should state variables always change with time? No. We can have state variables assigned, for example, for the location of landmarks in the environment, right? So we can have the position of a certain chair, the door, a table, or any other object in the environment, which is included in our state. Even though these objects are static, our belief about the location can change time to time with the measurements we take, right? So example would be location of landmarks, chairs, doors, and so on. Now when we learn mapping of an environment, this will become handy, because when we map a given environment, the map would consist of many static objects, right? So we won't include them as state variables, and we will try to estimate those. Okay. Now the question is, why do we need to estimate state? Let's take an example. Let's say we have built an autonomous mobile robot and we need the robot to get a book from the library. Okay, so what do we need to know? Of course, the first thing we need to know is where the library is, right? So let's say this is where the library. Okay, what else do we need to know? So we should know where the objects or the obstacles in the environment are. Okay, and we need to know the robot location with respect to this map. So if the robot is, let's say, here, it will take a path like this. Okay, and if the robot is somewhere here, it will take a totally different path like this. On the other hand, if the robot is here, then it will take a path like this. So you can understand that robot localization or the robot location should be known at all times. So it needs continuous update, right? Even though the library and other obstacles, other static obstacles does not change with time, we need to know the localization of the robot, and depending on the localization, the motion commands will be different, right? So if the state is known, correct decision making is possible. Okay, so here I will say this is our robot, and robot localization should be estimated. All right. In the introductory lecture, we discussed that there are two main activities taking place regarding an autonomous system. That is, environment interaction is twofold. We gather information by sensors and we take actions by actuators. So the information gathered by the sensors will be known as measurement, and I will denote that with Z. Okay, and actions taken by the actuators, we call them as control, and I'm going to denote that by U with the T subscript. Okay, so for measurements, I can have examples such as camera images, sonar readings, IR range, and so on. Okay, and if you can remember, these measurements will increase knowledge about the environment as well as ourselves. And similarly, we can have control UT, and some of the examples would be wheel motion, or any applied forces to the system. Then we can have some high-level control such as object manipulation, and so on. And these control actions would make us lose the knowledge. Okay, so this is loss of knowledge. So when we are taking a measurement, we are actually passively observing what's happening. But when we are performing an action, or when control is being performed, we are actually doing something to the environment, or we are doing something to ourselves. So that's why the measurement would increase knowledge, whereas control would make us lose knowledge. Understood? All right. Now we are going to treat time discretely, right? That means, so we have t-axis like this, and all the interesting events will take place at discrete time steps. So we have 0, 1, 2, t minus 1 and t. All right. We are going to make an assumption that measurement is at t and control ut happen at these time steps. All right. And one more thing. Now for our convenience, we will assume that the control action will take place first, and then we take a measurement zt. Okay, so zt will happen after a split second of the control action ut. Okay, so visually it's like, let's say we have our previous state xt minus 1, and from the previous state together with some control action we will have the next state, and we will take the observation after that. Okay, so again I'm telling you, both ut and zt occur at the same time, but for our convenience or learning purposes we will treat it as the control action taking place first, and after a split second the measurement would happen, zt. All right. And when it comes to control, there is one other interesting thing that we consider, that is, even though we take measurements all the time, the system might not take actions at each time step, right? Therefore, for consistency, we will consider do nothing as an action as well. Okay, so this will become clear when we do an example later. Since the state evolves with time, we can represent state transition as a chain of events. And the evolution of state is governed by probabilistic laws. So I will visually represent state transition as, let's say our starting state is x0, then we have x1, x2, and after a while we have xt minus 1 state, and then xt state. And we can also include environment interactions. So we have u1 and z1. Here we have u2 and z2, ut minus 1, zt minus 1, and finally ut and zt. So x would be state, u is control, and z is measurement. Okay. In general, the state xt is generated stochastically from the state xt minus 1. So by the word stochastic, we simply mean that the process is not deterministic, but some random nature is associated with it, right? So therefore it makes sense to attach a probability distribution for the generation of state xt. Now let's say we want to estimate state xt plus 1. So we need xt plus 1 state to be estimated. So ideally we should be needing all this previous information, that is all the previous states, previous controls, and all previous measurements to estimate the next state xt plus 1, right? But we are going to introduce a concept called complete state, where we say that a state is complete if we don't need any past states, past measurements, or past controls to predict the next state. So basically a complete state is like a summary of all what has happened in the past, right? So if xt is a complete state, That means it contains all the information, or it's like a summary of all the previous states, previous controls, and previous measurements. Okay, so the next state will depend only on the current state, and if we can forget all these past events, then we are going to call this as a Markov chain, right? So xt plus 1 state is going to be estimated using xt, and of course if there are any controls at that time step, we will be using them as well. So we are going to drop all these ones if we have a complete state, right? So this is the Markov assumption, right? So now in reality, it's very difficult to have complete states because that needs many state variables to be included in the state to cover all aspects of the system. And as a result, the computational complexity would be very high. Therefore, we make certain assumptions and pick a handful of state variables or a little more than that and treat the state as a complete state. Understood? So it was mentioned before that the true state of the system plus the environment is not directly observable. In fact, if it was directly observable, then we would not have been learning all these, right? For example, we know that if we take a GPS measurement, it has noise associated with it. Okay? So in order to estimate the state, we are going to use three inputs. We will use control, that is UT, then we will use measurement, so that's ZT, and we will also use the previous state, xt minus 1. Okay, and we are going to use all these three inputs in a probabilistic state estimation algorithm to obtain the next state xt. Okay, so in probabilistic approach, all these variables will be modeled as random variables, right? So this xt and xt minus 1, as well as this control, measurement, and the previous state. So all these will be modeled as random variables. Okay. So I hope that you are not new to random variables. So if I ask a quick question, what's the difference between a variable and a random variable? So both can take a set of possible values, but the values a random variable will take has probabilities associated with them, right? So for example, if let's take a random variable x, and if x is having a Gaussian distribution, then it would have a probability density function, something like this, right? So this is a Gaussian random variable. So we know that the values around this area or the mean has higher probability of occurring, right? So higher probability values. Okay. So if I repeat, the control U, the measurement Z, and state X. So all these are going to be modeled as random variables. Okay. So recursive state estimation is nothing but taking a feedback from the current state and feed that back into the system for the next time step. So this is our feedback, and this loop will go on and on. Okay. Let me take a couple of examples. So first, let's say we have a mobile robot and our objective is to make it autonomously navigate in a known environment. So known environment means we already have a map of the environment. Okay. So in order to achieve that, what we need or what we should estimate is the localization of the robot, right? So out of all the state variables regarding a mobile robot, we should select only the ones that are useful for this particular requirement. Okay, so I may write, first thing is choose appropriate state variable. Of course, we will discuss about this in detail later, but let me give you the idea. So if the robot is moving in an indoor environment, so let's say indoor, that is, we can say 2D or planar environment, then our state can have state variables xt, yt and theta t, where theta is the heading direction, okay, or the heading angle. And if you are dealing with let's say an outdoor robot, for example, we may have an unmanned aerial vehicle, UAV, right? So then our environment is 3D. So in that case, our state will consist of xt, yt, zt, the 3D position, as well as the orientation. So alpha t, beta t and theta t, and those are roll, pitch and yaw. Okay. The second example is to autonomously navigate in an unknown environment. So we would be needing a map of the environment. That is, the robot has to create the map as well as it needs to localize within that map, right? Now the problem is a little bit more involved than the previous example. Okay, so in this case, our state xt would have state variables for localization, just like before. Let's say we are taking a 2D plane environment, so we have x, y, theta for that. Plus, there should be state variables to represent the map as well. So we have x1, y1, x2, y2. So these are locations of the landmarks, okay, x, n, y, n. So now you can see we have a large set of state variables where this part describes the robot and this part describes the map. And here you can also see the latter part of the state has static state variables, right? So they does not change, but of course when we estimate it, our belief will change time to time. So here we are actually talking about a scenario where, so this is the robot x, y, and let's call this heading direction as theta, and then we can have some landmarks x1, y1, x2, y2. Okay. Alright, now we are going to have a recap on probability theory, and I hope you have already covered most of these materials before. However, we will learn a few new concepts as well. So when we discuss probability, we will be dealing with two domains, a discrete and continuous. So in a discrete domain, the space of all the values that a random variable x can take will be discrete, and the probabilities are always going to be non-negative and they will sum up to 1. Okay, and if we take a simple example of a coin flip, the space would contain head and tail, and if the coin is fair, then we know that the probability of x being head will be 0.5 and probability of x being tail would be 0.5 as well. In the continuous domain, continuous spaces are characterized by random variables that can take on continuum of values, so there will be infinitely many values, right? And that is why we cannot assign a probability for a single value, and we deal with probability density functions instead, right? So just like discrete probability distributions always sums up to 1, a PDF or a probability density function always integrates to 1. And when we want to find out a certain probability for a region A to B, then we will integrate from A to B, and this you already know. And a simple example would be finding the probability of the height of the students. So the equation here would tell us the probability of the students belonging to the range of 150 centimeters to 180 centimeters. Okay, now we will use the terms probability, probability density, and probability density function interchangeably in the future materials, and we will silently assume that all continuous random variables are measurable, and all such continuous distributions actually possess densities. Okay. The joint probability is the probability of multiple events happening simultaneously. So we can write it as Pxy, that is P random variable x taking the value of simple x and random variable y taking the value of simple y. And this is equally applicable to discrete and continuous cases. Now, if x and y are independent, then we can write the above as a product of individual probabilities or densities. So we have the x and y, or the joint probability of x and y. So that would become x equals simple x times random variable y taking the value of simple y, or simply we will write this as px times py. Okay, let's take an example. Let's say x denotes the color of the eye and y denotes the gender. So we have eye color, and it can take the values of black, blue, brown, and any other color, and we have gender y, male and female. We know that there is no connection between eye color and gender, therefore x and y are independent. Okay. Next, we are going to look at conditional probability. Often we notice that some random variables carry information about other random variables. Suppose we already know that random variable y's value is simple y, and we would like to know the probability that random variable x's value is simple x, condition on that fact. So we call it as the conditional probability, that is the probability of event x given the knowledge of event y. And we can write it as, in the discrete case, we have p x y, so this is the conditional probability, and it is equal to p x y, the joint probability, divided by the probability of y. Okay, and in the continuous case we will be looking at probability densities. So we have p x y, which is equal to p x and y, the joint probability, divided by the probability density of y. Okay, now if x and y are independent, we can write this as p x given y is equal to, the joint probability would become the product px py divided by py, and these two will cancel off and this would become px. So here we can see that y tells us nothing about the value of x when x and y are independent. So there is no advantage of knowing the value of y if we are interested in x in this case. The next concept we will look at is the total probability, or we call it as marginal probability because it appears in the margin of a table when total probabilities were manually calculated back in the days. So in the discrete case, the total probability theorem can be given as, so discrete px equal to the joint probability pxy summed over y, or else using conditional probabilities we can write it as px given y times py. So it's the same thing. Okay, so this is basically adding up all the probabilities such that when y1 happens, what's the probability of x happening, and when y2 happens, what's the probability of x happening, and likewise when yn happens, what's the probability of x happening. Okay, in the continuous case we have px, so here we are talking about the densities, so pxy dy, so we are taking the integration, and similarly using conditional probabilities we can write it as pxy py dy. Okay, next we will look at Bayes' theorem, which I suppose you already know. So first let me write for the discrete case. So we have px given y, which is equal to py given x, which is like the inverse, times px over py. Okay, we can write the same thing using the total probability theorem. So on top we have the same thing here, and at the bottom we can replace py using the total probability theorem. So let's take py given some x dash px dash. Okay, and in the continuous case we will have pxy, and on the right hand side we have py given x times px over py, which is also equal to pyx times px over, so here we have the integration of the total probability theorem. So y given x dash p x dash dx dash. Okay, now Bayes' theorem plays a dominant role in the probabilistic approach when it comes to autonomous systems. Now if you look at the terms, this one over here, we call it as the prior probability. So this is px. So it's like the prior knowledge we have, that is before incorporating any knowledge y into this probability, right? And on the left hand side, what we have here is known as the posterior probability. So posterior probability, this one. Okay, so I will write that again, pxy. Now posterior probability gives us a better estimate about x, because here we are incorporating some knowledge of y. So definitely px given y should give a better estimate than px, the prior probability. Okay, so this one is the posterior and this one is the prior. So we will be using the Bayes theorem to compute the posterior probability using the prior probabilities and any other probabilities that we have. So in the Bayes theorem, let's take x to be our state that we want to estimate, and we can take y to be all the controls, the measurements and the previous states. So y will be the joint event of all these. Okay, this is the joint event. All right. An important observation is that the denominator of the Bayes rule py does not depend on x, right? So for any value of x here, this py would be the same. Therefore, we can write the same equation as pxy some normalizer eta times pyx px. Okay, so this here is a normalizer. Okay, so we will freely use the same eta in different equations to denote normalizers, even if the actual values differ. All right, and actually we don't really need to find the normalizer most of the time, but if we want to find it, we can do so, because we know that a probability density function would integrate to 1, right? So if we do that, we can find this normalizer as well. Okay. Now it is perfectly fine to condition any of the rules discussed so far on arbitrary random variables such as the variable z. So if you take the total probability theorem, what I mean is we take the total probability theorem, let's say px, okay, and let me write it like this, which is equal to px given y times py, right? So what I'm saying is we can condition this whole equation by adding a random variable z, and also here we have z, and here we also have z. Okay, now I want you to check this or prove this as an exercise. Okay, so if you take a look at this again, we had the total probability theorem, right, that equation. So we have conditioned the whole equation using another third random variable z. So here we have that z, here we have that same z, and here we also have the same z. Understood? In a similar fashion, I can condition the base rule using a third random variable z. That is, we have p, x, y. So this is the base rule we know, p, y, x, and px over py. And when I condition it using z, I have z on the left hand side, and here also I have an z, and x will be conditioned on z, and y will be conditioned on z as well. Okay, so again the proof can be done as an exercise. Okay, next we are going to look at the concept of conditional independence. If x and y are conditionally independent given the knowledge of z, we can write the following equations. Okay, first we'll write the equations and then we'll try to understand. So the first one would be px given y and z would be equal to px given z. Okay, so here we see that y does not provide additional information when z is present. Okay, when we know z, y does not provide any additional information. And similarly, the second one would be py given x and z will be equal to py z, and we can say that x does not provide additional information when z is known. Okay, so you can see z is playing a role here. Generally, x and y might not be independent, but when we have the knowledge of z, then x and y are behaving like they are independent. So that's why we say that they are conditionally independent. Given the condition of z, x and y are independent. So the result would be, we will get an equation like this: px and y joint event given z will be equal to pxz times p yz. Okay, so I will let you do that as an exercise. But you can see that this is similar to absolute independence, right? So absolute independence is, if you can remember, pxy joint event is equal to px times py, right? So that is the absolute independence, and in this equation it pretty much resembles this equation, and it appears as if this z conditioning variable appearing here, here, and here. Okay, but unlike in the previous conditioning examples we had, that is conditioning of total probability theorem and conditioning of Bayes theorem, this will not always be true. Okay, so this happens only these conditions are given. Okay, so the conditional independence does not actually imply absolute independence, as well as the converse, that is the absolute independence will not imply the conditional independence. Okay, so if you are still confused about conditional independence, we will take an example in the next slide to clarify the things. Okay, as an example, let's take a random variable x equals height of a student, okay, and random variable y equals the vocabulary of that student. And let's assume that we are considering grade 1 students, grade up to, let's say, grade 10 students for this exercise. Now we see that when the height increases, the vocabulary level of the student is also increases. So what I mean by that is, a grade 1 student will have a small set of words he knows, the vocabulary will be small, but when he comes to grade 10, then his vocabulary will be large as well. So generally we see that x and y are not independent. So there is some sort of dependency, right? Now let's take a third random variable, z equals age. Okay, now we can see that when we know the age, we can actually guess the height, right? Of course, this is just an example, right? So when we know the age, we can guess the height, and therefore we can write an equation, the probability of certain x given y and z will be equal to the probability of x given z. So we can safely omit the random variable y. We will not need the amount of vocabulary to actually guess the height of the student if we know the age. Okay, so that's what it means by this equation. And on the other hand, we can also say the probability of y given height and age, so that would be more or less equal to py given z. So again, to guess the amount of vocabulary of the student, we might not need his height, just z or the age would be sufficient, right? So the conclusion is, the height and vocabulary seems to be dependent at first, but when we know the age, when a third random variable z is given, then we can thought of x and y, or the height and vocabulary, as independent, or else simply we say they are conditionally independent. Okay, so the condition is the knowledge of age, or z. Okay, so please take a moment to understand this, and with time you will get comfortable with the conditional independence idea. Okay. Now we are going to combine the concept of conditional independence with complete state. So if you can remember, we had this figure before, which is a Markov chain of the evolution of state. So here we have states, and we have controls u, and the measurements z, right? So if xt, the current state, is a complete state, then it is a sufficient summary of all what has happened in the previous time steps. Okay, at least we are going to assume that, right? So in other words, if we know xt, then all the previous measurements from z1, z2 to zt, as well as all the previous controls u1, u2 to ut, and all the previous states from x0, x1 to xt minus 1 will provide no additional information. Okay, so when we know xt, these will not provide any additional information to us. Therefore, we can write the following probability distribution. So we are interested in estimating the state xt plus 1 given all previous states, all controls 2t plus 1, and all measurements 1 to t plus 1. So this would be equal to So we take out xt, and we know that it is a complete state, and we are going to drop all the other states, and we don't need all the other previous controls but only the latest control, and we will not be needing any previous measurements but only the current measurement, and this happens because of this guy, right? So this is like the z, the third random variable we had in the previous slide, right? So if we know this guy, then there is no point keeping all these previous states, all the controls, or all the measurements. Okay, this guy provides all the information we need. So the remaining two would be the latest control and the latest measurement. Okay, so we can also say that the state xt plus 1 and the states x0 to t minus 1 and the controls 1 to t and the measurements z1 to t are conditionally independent given xt. Okay, so this is like, this is x and this whole joint thing y, and this guy is like z. Understood? With the revision of probability theory, now we are ready to look at our first probabilistic state estimator, the Bayes filter. First, I will introduce you to the Bayes filter. So here you can see the algorithm for the Bayes filter, and we will look at what its inputs and outputs are. We will understand the terms, and finally we will derive it. So the first thing you will notice is the word bell, and it stands for belief. Okay, so belief is given by belief xt is the probability or probability density of state xt given all the measurements and all the controls. Okay, so here we have not included the previous states as they are again estimates and not something we are provided with. Okay, then we have bell xt minus 1, and that's simple. We just substitute t with t minus 1 in the previous equation, so that is going to be xt minus 1 given z1 to t minus 1 u1 to t minus 1. Okay, so I will say this one as belief. Finally, we have bell xt bar. So bell xt bar, and that is actually bell xt without incorporating the latest measurement zt. Okay, so it's same as bell xt, but we are missing the latest measurement. So z is from 1 to t minus 1, but we'll be having all the controls. Okay, so these are just definitions. Okay, so here I would write before incorporating zt. So in the Bayes filter, you can see we give previous belief, current control, and current measurement as inputs, and the filter would output the current belief, bell xt. Okay, To derive the Bayes filter, I'm going to use the Bayes rule. In fact, the conditioned Bayes rule. So we had P A given B C is equal to P B given A C times P A given C over P B given C. So C is acting like the third random variable for conditioning, and this C can be the joint event of C1, C2, C3 and so on. So there can be many events joined in C. Okay, now let's take A to be xt and B to be zt and C to be z1 to t minus 1 and u1 to t. Okay, so shall we substitute those into the conditioned Bayes rule? What do we get? So we will get, so for A we have xt given B is zt and C would be z1 to t minus 1 and u1 to t. Okay, actually this one is z1 to t, right? And this is equal to P, so B is zt given A is xt and C is z1 to t minus 1 and u1 to t, okay, times P A is equals xt and for C we have z1 to t minus 1 and u1 to t, and in the denominator we have B is equal to zt given z1 to t minus 1 and u1 to t. Okay, so that's by substituting those values. Now we know that xt is a complete state, so we are going to assume like that. Okay, xt is complete. So if xt is complete, what can we infer from that? Now here you can see we have xt. So xt is a sufficient summary of all what has happened before, right? So this guy would not provide any additional information. So we can safely drop this guy, okay? And similarly, this guy will not provide any additional information either. So we can drop this guy as well. So this will remain and we will drop these. Okay, here xt is on the left hand side, so we can't do much about that. And what about this one? Now if you can remember, for estimating xt or for whatever xt, this guy is going to be a constant, right? So this acts like the normalizing constant where we can put eta here, right? So if we do all those things, we would end up with, so left hand side is actually the belief, right, of xt. That's how we defined it. and the first term would be pzt given xt, and we can drop all the remaining stuff there because xt is a complete state. And we have p xt z 1 to t minus 1 and ut. Okay, and in front we have the normalizing constant, and now you will understand why we defined something called Bell xt bar. Okay, so here the latest measurement is not incorporated, right? So we just defined it as Bell xt bar. So this is going to be our first equation. Okay, so you can see we have an expression for Bell xt. So this is actually what we want. So there is eta, and we have this probability or probability density, and we have Bell xt bar, which we don't know. So in the next step we would need an expression for this guy. Okay, next we are going to compute Bell xt bar, which is given by this probability distribution, and for that we will use the total probability theorem, and in fact the conditioned total probability theorem, which is given by this equation, right? So I can write p xt conditioned by z 1 to t minus 1 to u 1 to t. So this is Bell xt bar. So from the conditioned total probability theorem we get the integral p xt conditioned by z1 to t minus 1 and u1 to t, but we will have a new variable and we will take that as xt minus 1. Okay, so please follow the condition total probability theorem. We are just writing the same thing here, and the next term would be p, and we are going to take that new random variable xt minus 1 conditioned by the measurements up to t minus 1 and u controls up to t dx t minus 1. Okay, so you can compare this with this equation first. Okay, so here this y is actually xt minus 1. Okay, now we know that xt minus 1 is also a complete state. It is a summary of all the previous states, controls and measurements, and with that what can we infer? So here you can see we have xt minus 1 here, and as a result there is no need to keep this measurements. So all this is captured in xt minus 1, so this is like redundant and we can drop it, right? And what about controls? So up to t minus 1 controls are also captured here. Okay, so we can get rid of controls up to t minus 1, but one last control will remain, that is ut. Got it? Alright, so shall we write it now? So we have p xt conditioned by x up to t minus 1 and u1 to t, it's the same left hand side, and here we have p xt and we have the complete xt minus state, and I'm going to drop all the observations. There's no need of that. And I'm going to drop controls up to t minus 1, and what remains is ut. Okay, and we can write the remaining term xt minus 1 and z1 to t minus 1 and u1 to t dx t minus 1. Okay. Now another thing to note is that when we consider ut, this guy, okay, so it is like a future control for xt minus 1. So this is the state at t minus 1, but this is like a control which is future to this guy. Okay, so what can we do from that information? So if you look at this term over here, we are trying to find the probability density of xt minus 1 conditioned on these measurements, of course. And in this control, there is one control which is in the future to this guy. Okay, and we can confirm, or we can understand that ut has nothing to do with xt minus 1. Okay, so whether we have ut or not, that does not change this probability distribution, because we are talking about state at t minus 1. So as a result, we should be able to drop that ut as well. Okay, so it's also redundant and it's going to change nothing, right? So let me write that as well. So ut is a future control for xt minus 1. Therefore, it can be safely removed. Okay. Therefore, we can write the right hand side again. P xt minus 1 ut, that is the first term. But in the second term, I will drop ut, and what remains is controls up to t minus 1. Okay. So the left hand side is actually Bell xt bar. Okay, that's where we started. And this would be equal to the integral of p xt minus 1 ut times, so what is this over here? This is Bell xt minus 1, right? So we can write this as Bell xt minus 1 dx t minus 1. Okay, so that's going to be our second equation, right? So with that, the derivation of the Bayes filter is complete. Here you can see the algorithm for the Bayes filter once again, and now you can relate to these two expressions where we first derived this one for Bell xt, and this intermediate term here was derived in the second step, that is the Bell xt bar. Okay, so we call the first step as the prediction and the second step as the correction. So you can see in the prediction step, we are using the previous state together with the control input to do a prediction which goes into this. Okay, and in the correction step, we can see we are incorporating the measurement. Okay, in this step, we are using the previous state and the control input, and in the correction, we correct what we have predicted in the previous step using the measurement. So this is an iterative process which goes on and on. Okay, now since it is an iterative process, we have to start somewhere, and we need initial belief px0 to start the base filter, and we will be needing the control input and a state transition model for this step together with its probability distribution, and then we need the measurement with the measurement model, and here you can see we need its probability density function as well. Okay, so basically this is all there's to it in the base filter. So the base filter we derived is for continuous spaces, and when we are dealing with discrete case, we need to add a for loop here for all x do, and here we have the end. Okay, and the integration would become a finite sum over here, and we don't need this guy, right? So let me write for discrete add for loop to go through all x. Okay, so some special remarks about the base filter is that due to line 3, actually, even though it was nicely derived on paper, the practical usage of the base filter is very limited because it's very difficult to obtain a closed form solution for this step when we are having this integration. Okay, therefore we use the base filter in very limited applications. But the good news is we can transform base filter to a tractable version with certain assumptions, which we will discuss later. So I believe until we do a solid example, these concepts that we discussed would still sound abstract. So let's do an example using the base filter now. First, let me explain the setting of this problem. So here we have an autonomous mobile robot, and it needs to estimate the state of the door, whether the door is closed or open. Okay. So the system has a sensor, let's say it can be a camera sensor or any other sensor, which can get observation about the door. And it also has some actuators which it can use to push the door. Okay, so our ultimate goal is to find out whether the door is open or closed. To begin with, we will make two assumptions. So first, we will assume that the door has only two states, open and closed. Okay, and the next assumption is that the door state changes only by robot. That means there are no humans in the environment to open and close the door, and also there are no environmental factors like wind to change the state. Okay, so only the robot will change the state of the door. Next, we can have certain probabilities assigned to different events. So to begin with, let's say we don't know the initial state of the door. So initial door state is unknown. Okay, so in that case, we will assign equal probabilities to bell x0 open and bell x0 close. Okay, so definitely this will add up to 1. Okay, and the next probabilities we are given with is for the robot sensor. So the robot sensor is noisy, and let's carefully go through these probabilities one by one. So the first one here says when the door is open, detecting the door to be open by the sensor has a probability of 0.6. So I hope you understood what that means. When the door is open, detecting it to be open by the sensor is 0.6. So obviously when the door is open, detecting that the door is closed should be 1 minus 0.6, that is 0.4. Okay, so here also we have the sum equals to 1. Okay, and similarly, if we take this final one, when the door is closed, detecting that the door is closed by the sensor has a probability of 0.8. Okay, so that means when the door is closed, detecting it as open would be 1 minus 0.8, and that should be 0.2. So these two will sum up to 1 as well. Okay, so you can understand that you don't actually need all the 4 probabilities to be given to you, right? So if you have 2 of these, you can find the rest. Okay, now if I ask a quick question about the sensor, can it detect a closed door or open door more reliably? So we can see that the probability of detecting a closed door here is 0.8 versus here open case is 0.6. So that means the sensor can detect a closed door more reliably than an open door. Let me write it here. So detects a closed door more reliably. Okay. We need few more probabilities before we start to use the Bayes filter to this problem. Now if we consider the actuator of the robot, it is given that it is not 100% reliable. Okay, so let's go through these probabilities again one by one. So the first one says when the door is open, the actuator will push, and the next state of the door becoming open would be 1. Now that's obvious because previously the door was open already, and we are also trying to push it, and the next state becoming open would be 1, and therefore this guy would become 0, right? Because these two would add up to 1. And next we have a closed door, and we try to push. Okay, and the next state of the door becoming open is given as 0.8. That means 80% probability is there when we push a closed door, the door becomes open. Okay, and here again the door remaining in the closed state even though we have pushed will be 20% or 0.2. Okay, these two would add up to 1 as well. Now if you can remember, we discussed about a do nothing action as well. So here what we have is when the door is open, we do nothing and the door remains in the open state. So that should obviously be 1, and this one should be 0. And similarly, when the door is closed, we do nothing and the door remains in the closed state would be 1 as well, and this would be 0. Now these probabilities may look trivial, but to implement the Bayes filter we need them. Okay, now we are ready to use the Bayes filter in this example. So let's suppose at time equals 1 the robot does nothing, that is u1 is equal to does nothing, and it senses an open door. So z1 is equal to sensing an open door. So we can use Bayes filter using Bayes filter. So the first thing I'm going to do is implement the third line, that is bell x1 bar. Okay, so this is equal to, so here you can see it from this line, so I'm just writing this line. Okay, so bell x1 bar equals sigma p x1 u1 x naught, that is previous state, times bel x naught. Okay, and if I expand that, we get p x1, so u1 is actually do nothing, and for x naught we have two cases. First, let's take x naught is open, so this times x naught is open, okay, plus we have another case, so we have p x1 u1 equals do nothing, and x naught can be closed, okay, and this one is x naught equals is closed. So basically this step is a total probability theorem, right? So next what we are going to do is we will substitute for possible cases of x1. So we substitute for possible cases of x1. So x1 can be is open or is closed. So this basically comes from the for loop part. Okay, all right, moving on. So here I have what we obtained in the previous slide, so we'll continue from that. So we need to substitute for possible cases of x1. So I will start with L bar x1 is open. Okay, so here we are actually talking about substituting for this one. Okay, so if we substitute that, what do we get? So this probability, when the door is open, we do nothing. What's the probability of x1 being open? So that was equal to 1 because it was given, remember, right? Open door, we did nothing, therefore the next state becoming open is equal to 1. So this is equal to 1 times, next we need this guy, bel x naught is open. So at the beginning we didn't really know whether the door is open or not, so we assign 0.5 for that. So this will be 0.5, okay, plus next we have this one. So x1 is open, so we have a closed door, do nothing, and next state of the door being open. So this probability we already had earlier to be 0. Closed door, we did nothing, and we are expecting an open door, right? So that probability would be 0 times, next we need bel x naught is closed, so this also had the probability of 0.5. okay, so here we have 0.5, so this will give us 0.5. okay, so this is bel bar x1 is open, right? Now the next one is the case where bel bar x1 is closed. So we can do the same reasoning as before and calculate it, or else we can just obtain that from the previous probability, because that would add up to 1. Okay. Anyway, if I do the probabilities here, I would have 0 times 0.5 plus 1 times 0.5. So please do that just like in the previous case. So here we would get 0.5. But anyway, you can see we don't need to do that calculation here, because we can get it by the addition of 1. Okay. This can be done because the DOE has only 2 states, right? Now looking at these answers, we see that bell bar x1 is actually equal to bell x0. So here also we have 0.5 and 0.5. Now that should not come as a surprise, because the action was do nothing. Okay, so the prediction with do nothing action would give the same probabilities, right? So this is no surprise, because of do nothing action. All right, so our next step in the Bayes filter is to incorporate the measurement, this step. Okay, so here we have the control input, and here we have the measurement to be incorporated. Okay, so let's do that part as well. So I will write incorporate measurement. So from the Bayes filter 4th line, I will write bell x1 would be equal to the normalizer eta times p. Now the observation was sensing an open door, therefore z1 equals sense open. Okay, given state x1, bell bar x1. So I just wrote this 4th line here, right? It's the same thing here. Okay, now using the for loop, we have to do this for each x1. Okay, so that means first we'll take bell x1 is open, that one, so that will be equal to eta times. So when x1 is open, detecting that the door is open, so we had a probability for that, so that was 0.6. okay, so here we have 0.6, and next we need bell bar x1, and we calculated it here when x1 is open, so this is that one, so it is 0.5, right? So I would write 0.5, which came from here. Okay, so this would give me eta times 0.3, and second one, bell x1, the state of the door estimated as closed, would be equal to eta times, now we need closed door sensed as open. Okay, so that probability was 0.2 if you go back and check, times bell bar x1 when x1 is closed, so that comes from this line here, so it was also 0.5, right? So this is 0.5, so this is equal to eta times 0.1. all right, so the final step would be to calculate eta, and we know that this would add up to 1. Okay, so we have eta times 0.3 plus eta times 0.1 equals 1, and that would give us eta to be 2.5. okay, so with that eta, now we can actually calculate the first one to be 0.75 and the second one to be 0.25. so here are the answers, right? So this means at time equals 1, the probability of the door being open is 0.75 and the probability of door being closed is 0.25. so we started with 0.5 and 0.5, and with the control action and the observation we ended up with these probabilities. Okay, now you can also see that even without calculating eta, we could have obtained that, right? So these are the exact probabilities, but we could have gotten an idea from this as well. Okay. Okay, now suppose at time t equals 2, the robot pushes, that is u2 equals push, and it senses an open door. So z2 equals senses an open door. So I want you to do the same thing, just like we did before, to use the base filter and complete the steps. So this is an exercise. Okay. When you complete the steps, you should be able to obtain belief x2 for the state of the door. Okay, so please complete the steps as an exercise, and I will upload an illustrated version of this example so that you can compare your final answers. Okay, with that we have come to the end of this lecture. Let me summarize what we studied. So state estimation is very important for autonomous systems to perform well. We studied the concepts of state, state variable, state transition, complete state, and finally state estimation. We revisited the theories in probability, and we understood that Bayes' theorem and conditional independence play a major role in probabilistic approach when it comes to autonomous systems. And finally, we derived our first state estimator, the Bayes filter, which is a probabilistic method for estimating state in recursive manner. Thank you.